Yes, welcome everybody to the second talk this morning. The speaker is Dr. David Blewett of the Johns Hopkins University Applied Physics Lab. David, he's researcher, senior researcher at the Applied Physics Lab, and he did his undergraduate at the University of Pennsylvania in astronomy and astrophysics. And he went west to Hawaii to do his graduate study in geology and geophysics. So as a consequence, he spent some time, I think, in Antarctica. He got the Antarctica Surface Medal, and then he went on to work for NASA. I mean, on the NASA program. And to cut it short, David is an expert on planetary science, and he worked a lot on Mercury, and then he participated in the Messenger mission in the science team, and he has an asteroid to him, asteroid 8897 is named after David Blewett, and we will listen to him because he's going to talk about his mission on called Vertex. It's a very interesting mission. Have a lander on this matter anomaly region called Lunar Gamma. So I really know. Oh, by the way, David, I have leave a little bit early because I have another place to go. So Dr. Ian Lai would moderate your talk, for your question and answer session later. Yeah, David, please.
Yeah, so I'm really happy today to be able to talk to you all about this Lunar Vertex mission in particular, and the PRISM program specifically. So this is a mission to Reiner Gamma. So why would we want to have a mission to this particular place on the moon called Reiner Gamma? Shown here are two views of this marking called Reiner Gamma. One on the left is color composite of Clementine images taken with the sun fairly high in the sky. And on the right is from the Lunar Reconnaissance Orbiter wide angle camera, a mosaic put together with the sun at lower in the sky. So, you can see the shadows are cast. You can tell that impact craters are holes in the ground. And this curious sinuous marking that you see there, doesn't seem to have any topography. So it's a very interesting feature. It's been a puzzle for a long time, and so I'm going to go into some of the history of Reiner Gamma and why you might want to have a mission to such a place. Yeah, so it's Reiner Gamma is the type example of what has come to be called a lunar swirl. This is a long-standing puzzle in lunar science. It was seen in early telescopes, and in fact, people at first thought it was a crater, and it was given the name Galileus after Galileo. However, as telescopes improved, and then certainly once photography came in, people realized that it's not a crater. The tail that extends there up to the northeast, it doesn't look like a normal crater ray. It's not a ridge of higher albedo Highland material because it doesn't cast a shadow. And so actually another crater was given the name Galileo or Galileus. And this feature came to be called Reiner Gamma for a nearby impact crater, the crater Reiner. So here are some further historical photographs that illustrate Reiner Gamma and why it's so interesting. So yeah, as I said, that improving ground-based telescopic images revealed it to be just apparently superficial albedo marking. I love these two pictures on the right from the rectified lunar atlas. One at high sun, taken in 1960, a photographic plate image, and down there on the bottom, look at that, Mount Wilson more than 100 years ago. A picture taken, at lower sun, where the shading and topography shading and shadows allow you to see the topography of the surface. So yeah, Reiner gamma is just this enigmatic, high reflectance surface marking of unknown origin. Yeah, well, as time went on, we got to the space age, and it was discovered that there are swirls on the far side of the moon as well. This is a picture from Lunar Orbiter 2 from 1966, and it shows the extensive swirl marking on Mare Ingenii. So then just a couple years later, in 1968, this is a picture taken by the Apollo 8 astronauts. So this was the first time that people went to the moon in Apollo 8. And you can see the extensive swirls that extend across Mare Marginis and go across the brightest feature there, kind of in the center top, is the crater Goddard A. So additional, spectacular examples of swirls on the far side. And just a year or so later, this is a picture taken by the Apollo 10 astronauts, the second time people went to the moon. And this demonstrates that there are swirls in the lunar highlands, not only the sort of the flat lunar Mare plains, but swirls can be found on the highlands. This is an oblique view looking to the side there near a crater called Firsov. Yeah, okay, so yeah, back to Apollo. So I talked about Apollo 8, Apollo 10. Well, the Apollo 15 and 16 command modules released sub-satellites that contained magnetometers. And these were in mostly equatorial orbits. But they discovered that there are patches of, magnetized crust on the moon. And the strongest one that they mapped out happens to coincide with the Reiner gamma swirl. So that's, very interesting, right? That there's this area of magnetized crust that corresponds to this unusual high reflectance marking. Yeah, so later mapping from spacecraft, in particular, the Lunar Prospector mission that flew in around 1999-2000, that was in a polar orbit, so it could map the magnetic field of the moon, over the entire moon. And so we found, a number of other of these areas that have come to be called magnetic anomalies. And their origin is unknown. So now I'm going to go back to the swirls and talk about the hypotheses for how they may have formed, and then I'll talk about the hypotheses for the origin of the magnetic anomalies. Okay, so how do we get these funny, sinuous, bright markings on the moon? Well, one idea is what's called solar wind standoff. And the idea here is that the presence of the local magnetic field attenuates the flux of the solar wind that reaches the surface. So this slows down the normal space weathering or soil darkening process that happens elsewhere. And I'll come back to say a little bit more about space weathering in a minute. Another idea has to do with impacts related to a comet. So this idea is mainly from Pete Schultz, who's at Brown University. And the first idea that Pete had is that gas and dust in the coma of a comet modifies the surface. And kind of a variant of that is from Patrick Panay and Larissa Starkina and others. Has to do with an impact of the fragments of the nucleus of a comet or a meteoroid swarm associated with the comet kind of scours and plows the surface, exposing fresh material. Then a more recent hypothesis has to do with unusual dust effects. And the idea here is that there can be electric fields that are induced by the interactions of the solar wind with the magnetic anomaly. And this could cause electrostatically lofted dust particles to either be attracted or repelled from certain locations. These unusual dust motions could possibly, in another idea, modify the photometric behavior of the surface by sort of collapsing the so-called fairy castle structure of the very uppermost surface. That's the very highly porous sort of dust filaments that can form in an airless environment. And then another idea is some sort of actual magnetic sorting of dust depending on its content of nanometer size iron particles. That these magnetic forces could actually be physically separating the dust, and that maybe the swirl corresponds to an accumulation of this bright high reflectance dust. Okay, so then in the next slide, the next couple of slides, I talk about space weathering a little bit. Okay, so here to illustrate this, we've got two craters that are just about the same size that are found in the same type of terrain in the south central highlands of the lunar near side. So the crater on the left is Tycho. It's morphologically fresh. You can see that it has a very sharp rim and central peak. There are very few, if any, sizable craters that are superposed on top of it. And it has very extensive rays extending out from it. Now, on the right is Pitiscus, a crater that's just about the same size, but you can see that its rim and central peak are highly rounded. And there are a number of superposed craters on top, and it does not have any rays, okay? And so what we see from examples like that is that impact craters that have a sharp morphology have bright interiors and bright ray systems, whereas craters that are older, that is, they've been exposed to the erosional effects of impacts for a longer time, they lack the rays. Well, this indicates that there must be some process that causes the rays to fade away with time. Otherwise, I guess every crater would have rays, or actually maybe no craters would have rays, because the material dug out and deposited from a new crater would have the same reflectance as all the background, and you couldn't see the contrast of the material between the ray material and the background on which it was deposited. So this process is called space weathering. And this affects the surfaces of airless bodies throughout the solar system, and it complicates the interpretation of remote sensing data. Is a surface bright because it's inherently bright, or is it bright because it is young and hasn't been subjected to a lengthy period of space weathering? Now, it's generally thought that the two agents that cause the space weathering, soil darkening, are exposure to the soil wind and sputtering and implantation, and micrometeoroid bombardment. However, we don't really know the relative roles of these two things, which is really more important. However, at a lunar magnetic anomaly, we have a natural laboratory which allows us to control for one of these variables, because the local magnetic field will attenuate the solar wind flux, but it will not affect micrometeoroid bombardment. So a lunar magnetic anomaly is really a great place to go to learn more about this solar system-wide process of space weathering. So here I jump back to, okay, so we've got this magnetic anomaly. Where did it come from, right? So that's a separate puzzle from the origin of the swirls, really. And again, there are a handful of hypotheses having to do with the origin of the magnetic anomaly. One that is promoted by Lon Hood and some of his coworkers has to do with magnetized basin ejecta, right? The formation of a basin-size impact crater on the moon, you know, a crater that's bigger than maybe 200 kilometers in diameter or so. Lunar scientists call that a basin. So for big basins like Imbrium or Orientale or Crisium, those are tremendously energetic events. They would have created huge amounts of melt and vapor and plasma. And the idea here is that this plasma cloud could have expanded around the moon and converged on the antipode, the point diametrically opposite the impact. And in that process, any ambient fields could have been amplified. And therefore, this materials that are deposited near the antipode would be subjected to this enhanced amplified magnetic field. Now, a second idea has to do with a comet impact. And if you'll recall, when I was talking about the origin of the swirls, there's this idea that the impact of a comet's coma onto the surface could have modified the surface and thereby created the high albedo reflectance marking. Well, the Pete Schultz hypothesis wants to create the swirl and the magnetic anomaly in the same event. And Pete's idea is that plasma associated with the coma, again, when that plasma is compressed against the surface as a comet collides with the moon, that the comet's field or ambient fields, again, can be amplified, and that this magnetic field would be impressed on the surface materials in the region of the coma's collision. Then a third idea, you know, has to do with an internal dynamo. Maybe early in its history, you know, the moon does have a small iron core. Maybe it was convecting, creating a dynamo field, a global dynamo field, kind of the way the Earth's or Mercury fields are generated today. And so that any molten rocks that cooled in that time, whether they're impact melts or magmas intruded into the crust or lavas erupted onto the surface, if they cooled through their Curie points in the presence of those magnetic fields, the dynamo field dies away, and what we see in the magnetic anomaly is these remnant fields. And somewhat related to that, you know, could be, it has to do with what's the nature of the magnetic carrier in the moon rocks, right? And one idea from Mark Wazurek is that this could be related to debris from an iron-rich impactor, could be, you know, the carrier of the magnetic signal. Okay, and I think I know that this crowd is well-versed in space physics. So, you know, when we see these magnetized regions, they modify the interaction of the moon with the solar wind from what it'd be if the moon was just an inert dielectric sphere. As you all well know, you know, there's this varying plasma environment as the moon goes around in its orbit. You know, it's in the magnetotail or it's out in the open solar wind. And therefore, there are some interesting interactions that take place between these local magnetic fields and the solar wind plasma. Yeah, so you know, a variety of spacecraft observations have demonstrated that there are these standoff regions or mini magnetospheres that form over the strongest magnetic anomalies, you know, from reflected electrons, reflected protons, energetic neutral atoms, and so forth. You know, these are in the scale of magnetospheres throughout the solar system. You know, these are very, very small indeed, you know, compared to the magnetosphere of the Earth or Mercury or you know, even Mars. But you know, it's very interesting to look at the interesting plasma physics that's taking place in these very smallest of the solar system's magnetosphere. And of course, we don't actually know the flux and energy of the ions and electrons that reach the surface. Okay, so a point that I and some of my colleagues have been making for a number of years was that a lunar magnetic anomaly presents a great opportunity to study a range of problems in planetary science, right? And these range from geophysics, you know, what's the nature and origin of the magnetized crust, you know, and this, you know, gets to things like the ancient dynamo, magmatic intrusion, magnetized basin ejecta, you know, comet impacts, those must be happening on the moon and other bodies. The space plasma physics that I just talked about, you know, how does this change with time of day? What are the fluxes of the by energy and species that actually get down to the ground on the moon? And then the geology and surface processes, you know, space weathering, the implantation and sputtering by the solar wind, the origin of the swirls, you know, these dust motions, comet impacts, and, you know, possible rock types that have high metallic iron content, you know, that we don't have in our samples from either the Apollo, Luna, or Chang'e sample returns, right? Right. So, you know, I had been kind of making the case for the high science potential of a mission to a lunar magnetic anomaly. And apparently NASA was listening because they did, in fact, designate Reiner Gamma as the target for the first of the PRISM missions. The slide here, you can see on the right, and a map of the total field strength. That's the colorized portion overlain on the visible image from Lunar Reconnaissance Orbiter, and you can see how the magnetic anomaly, you know, lines up right with the albedo feature. All right, so I said that NASA designated Reiner Gamma as the target destination for the first PRISM mission. So what is PRISM, right? Well, this shown here is an excerpt from the announcement of opportunity that came out in November of 2020. And PRISM is a program that funds suites of science instruments to study a particular focused science problem. And this suite of instruments will be taken to the moon aboard a commercial lunar lander. And for the PRISM-1 opportunity, NASA had actually two deliveries, one to Reiner Gamma and a second one to a basin on the far side called Schrodinger, where of course there would be different science objectives than for a mission specific for Reiner Gamma. So this is one of the tables from the announcement of the opportunity, which has kind of the pertinent characteristics. So for this opportunity, NASA budgeted $60 million. So that is for these two missions. So essentially, if you were going to propose to do one of these, your cost cap, you know, was 30 million, right? And the mass was limited to about 50 kilograms. And again, the lander and the launch are not within that PI managed cost cap. The lander and the launch are furnished through separately. NASA pays for them through this commercial lunar payload services known as CLIPS. So here's a little bit more about that. So these providers, this set of 14 different companies that are qualified to bid on these delivery jobs, they're responsible for all the end-to-end mission activities, right? They integrate the science payload. They need to transport the payload to the moon, and so this includes everything: the launch vehicles, a lunar lander, any surface systems, the communications between the moon and the Earth, and all the associated resources. So the first 10 of these CLPS missions, the locations for the target of the missions have been designated. And what's really interesting is that the lander solicitation is issued after the selection of the PRISM science suite. So the PRISM payload accommodation requirements are included as a part of this request for proposals to which the CLPS companies respond. So this is very different from a typical space mission, right? Where the spacecraft is custom tailored for the set of instruments that it's going to carry. Here, these lander companies, they've got their standard model lunar lander, and they make some modifications to adjust for how the science payload wants to will be accommodated. But it's not as though it's designed from the very beginning for a particular science mission. But this is a way to lower costs and to have more frequent missions of this type. By having a commercial lander, it's a basic model, and we do the best science we can, given this method of doing business, which is quite different from a traditional NASA space mission. So this is a slide that I got from the NASA Lunar Discovery Program website. It shows all the CLPS deliveries that are scheduled from 2023 to 2026. The ones that have been awarded so far, there's a company in Pittsburgh, Pennsylvania called Astrobotic. They have 2 different landers. They're going to be delivering a CLPS payload with some NASA instruments to an area near the South Pole. And they're also delivering the NASA Viper rover, which is a large rover intended to explore permanently shadowed regions. There's a Draper. They won the delivery for that far side Schrodinger Basin mission. A company called Firefly is going to send a lander to Mare Crisium. And Intuitive Machines, which is a company in Texas, they have actually won 3 of these CLPS deliveries so far, including the Lunar Vertex Reiner Gamma delivery. That's their 3rd mission. So it's good from my perspective because they have 2 chances to land on the moon successfully before they're delivering my payload. Yeah, so in response to that PRISM call that you saw, APL, we put in a proposal. The cover of the proposal is shown here. And of course, because at that time we didn't know what the lander would look like, that's why the lander in this illustration is just kind of a ghostly outline. But we did show the CAD model for our own rover that we're going to be providing. So the science goals, that we listed in the proposal were three top ones were to investigate the origin of the magnetic anomaly, investigate the origin of lunar swirls, and to determine the structure of the mini magnetosphere. And we had some sort of ancillary goals, having to do with better understanding space weathering, the importance of micrometeoroid bombardment versus solar wind exposure, And then there are a few things that we could answer related to certain strategic knowledge gaps for human exploration. Okay, so yeah, anyway, our proposal was selected. It was one of 13 that NASA received. We were very fortunate. I was obviously very pleased that my proposal was selected. So to carry out these science goals, I think we can go to the next slide. And this shows the first part of our payload suite. So we have 3 instruments that are going to be on the lander. The first is an array of cameras. There's 3 clusters, each of which has 3 cameras. And these are going to provide a 360-degree view around the lander just for geologic context. And they are going to be radiometrically calibrated, so we can use the images to perform photometric modeling to derive information on the nature of the regolith. That camera set is being built by a small, relatively new aerospace company called Reiner, which is in Colorado. APL is building a vector magnetometer that will go on the lander. You can see it illustrated on the right. Up at the top of this 50-centimeter long mast is a ring core flux gate. And then down towards the bottom are 4 commercial mini magnetometers in a tetrahedral array. And that special arrangement allows us to sense the strength, direction, and gradients of any fields that come from the lander vehicle, which is very important because, of course, as I said, this is just a commercial lander. It wasn't designed from the beginning with a strong magnetic cleanliness program, right? I mean, they're going to do their best, but it's not as though, again, you had a spacecraft designed from the very beginning to have a very magnetically clean. And we have a ion electron spectrometer being built by the Southwest Research Institute. It's going to measure the ions and electrons that reach the surface in the energy range that you see there. So the lander will also deploy a small rover that we are buying from a company called Lunar Outpost, which is a very young new space startup, also in Colorado of the United States. The depiction of the rover is shown there on the left, with the Intuitive Machines lander in the background. And the photograph on the right shows an earlier prototype when it was being tested. This is a small rover. It's only about 35 centimeters tall. So the rover is going to carry 2 science instruments, a second magnetometer suite, again being built by APL, which consists of just the 4 commercial magnetometers in that tetrahedral array. You can see it there. It's kind of that top hat looking thing on top of the rover, or it looks like maybe a smokestack on an old steam engine. And then carried within the rover is a multispectral microscope. This is being built by a company in Toronto, Canada, called Canadensis. Again, a relatively new space player, but it uses active LED illumination so that we can study the structure, composition, porosity, texture, particle size of the soil. And of course, it's important to have a rover so that we can get away from the lander's rocket blast disturbance, because several of the hypotheses for the origin of the swirls would predict special textures, right? If the surface was scoured by a comet coma, or if there's an accumulation of very fine dust, we want to be able to look up close at the particle size and so forth. Yeah, so this just shows a little bit about our landing site. We're going to land there in the central bright oval of the Reiner gamma swirl, but close to the so-called dark lane that is just to the north. So you see the context image there on the right. And then on the left are lunar reconnaissance orbiter narrow angle camera images of our landing site, shown by the dot. The scale there is that circle is 200 meters in diameter. So we're going to make a traverse generally north towards the dark lane. And because our rover is very short, it needs to have line of sight radio communication back to the lander. So fortunately, there are very good topographic maps that allow us to create what's called a viewshed map, where you can, for an assumed antenna height of the lander, you can map out every portion of the surroundings that has line of sight to that location. So you can see there in the yellows and the blues, that is our nominal rover traverse path, which is about 1.2 kilometers long. Yeah, so I just thought I'd say a little bit about the name of the mission as we get towards the end here. So the Latin word vertex can mean swirl or vortex, or whirlpool. So that's good. We're going to go to a lunar swirl. But of course, in English, a vertex is an intersection, right? And as I see it, the magnetic anomalies lie at this crossroads or intersection of geoscience and the particles and fields domain of space physics. So that's really our mission's highly interdisciplinary, and that intersection is the kind of our theme. Yeah, so just a few conclusions. Lunar Vertex is the first PRISM mission. It's a landed investigation that's going to go to this unique environment of a magnetic anomaly. We're going to address key questions in major subdisciplines of planetary science that have to do with geophysics, space plasmas, planetary geology, and we're going to provide important information on the origin of the lunar magnetic anomalies, the interaction of the solar wind with the magnetized crust, the origin of the swirls, and the space weathering process on silicate regoliths. So some of our status. This is a very rapid development program. From the time that we were selected until landing on the moon is going to be about 3 years. We passed our preliminary design review in May of 2022. We had a critical design review in December of 2022. Flight builds for all the instruments and the rover are proceeding, and launch is expected in the first half of 2024. I have a few backup slides. Let's just see if there may be one or two of them I might want to mention. This is just an org chart. APL, we're responsible for the overall project management, systems engineering, safety and mission assurance, science, and the payload, and we're providing 2 of the instruments. I mentioned our partners that are providing the rover and the instruments. Now this is a close-up of the landing site. It's very flat. There are no steep slopes or no fresh craters, no boulder fields, so it's great for the lander safety. This is our science team. We think we've got a great team, which includes planetary geologists, space plasma people, geophysicists. We have some foreign participation with 2 foreign co-Is, 2 from Canada, 1 from Sweden, 1 from France. I'm really happy to have on the team Dr. Lon Hood from the University of Arizona. He's the first person who proposed the solar wind shielding hypothesis for the origin of swirls back in 1979. So it's really great to have him on our team. Let's see. maybe go one more. Oh, this is the Intuitive Machines lander that is going to carry our suite. Yeah, our cameras are mounted different places around the lander to provide the 360-degree view. One of those masts sticking up on the top there you see is our lander magnetometer. Our plasma spectrometer is mounted off to the side to give it a good field of view of the sky, you know, the path that the sun will take across the sky. And the golden boxes that you see are actually some other NASA payloads that this lander will be carrying, and in addition to our lander. So yeah, in addition to our rover. I should mention that there's a high energy particle detector from the South Korean Space Agency that will be on this lander. Again, sponsored by NASA or in cooperation with NASA. And the European Space Agency has a laser retroreflector that will be on the lander as well. So yeah, I should probably just stop there, and we can have any questions.
Yeah, thank you very much. And question from audience. You can raise your hand and or type in the chat box.
Yeah, while we're waiting to see if there's any questions, just something else I could say is that you know, this is as I said, this is a very low cost mission, and in fact, NASA does not even consider it to be a space flight mission. It's a research and technology project. So the amount of testing, documentation is far lower than for a typical, you know, NASA mission like Messenger or Lunar Reconnaissance Orbiter or Dragonfly. You know, far below that, with associated greater acceptance of risk, right? So that's the trade-off.
Okay, so two people, Jen Deka, please.
Hi, David. Thanks for the interesting talk. I was wondering with regards to your energy analyzers, whether you're measuring both plasma coming from basically towards the surface as well as away from the surface, or just whatever comes towards the surface.
Yeah, the field of view, the aperture, the field of view of the ion electron spectrometer is pretty much, you know, pointed at the sky. I think it has a 270-degree field of view, but it's essentially pointing up. Yeah, so I that's something we've talked about, but I don't think that we'll be able to sense any of the species coming up from the surface. But, you know, of course, you know, if this was just a mission out, you know, in space, you just point at the solar wind and the solar wind would come on in radially. But because of the, you know, complicated interactions, as you well know, that can take place here within one of these magnetic anomalies, these particles can be coming in, you know, from a wide variety of directions. So, you know, we have sort of a cross-track field of view, and then the sort of the main field of view that covers the area on the sky.
Okay, maybe one more, if I may, related to that. Unless I missed it, do you get the electric field from that, or not really?
Well, the electric field, I suppose there could be some, you know, sensing of that from, you know, the behavior of the electrons. We think will provide us with the kind of topology of the magnetic field, you know, above Reiner gamma. Electric fields, that's not something that we've considered so much. I mean, we don't have a specific electric field sensor, but yeah, you know, that's something for Jasper Halikas, you know, is our deputy PI, George Ho. Shahab Fatemi, you know, those guys could answer that question better than I could.
Thank you.
Yep.
So another question from Marshall Banks.
Hi, I posted in the chat, but basically I was wondering what if, so you can go there and measure the magnetic field and so on. What would you regard as a conclusive evidence for, say, the deflection hypothesis? I mean, so you we want to. Field. How do you know that's the physical cause of what you're seeing?
Right. Well, you know, as our rover drives, you know, we're going to be measuring the magnetic field. We'll know the orientation of the magnetic field, and from that we can get an idea of the degree to which these solar wind particles have access to the surface. And, you know, we expect that to, if the solar wind shielding hypothesis is correct, we would expect, you know, there to be a correlation in the direction of the magnetic field with the reflectance of the surface, right? So, you know, in places where the magnetic field is more, the field lines are more vertical, that we expect would give more access of the solar wind protons to the surface, whereas in areas where it's more horizontal, that would provide more shielding. So, you know, the micrometeoroid bombardment is going to be the same over this area. So if we see this evidence for, you know, the nature of the soil changing in concert with the nature of the magnetic field, then I think we could say that solar wind shielding is the predominant cause of space weathering, or the cause of the swirl.
So any other questions? Yeah, if not, we thanks David again. Yeah, very thank you to give a talk in TSU. Thank you very much.
I very much appreciate the invitation. Thank you for that. It was great to talk to everybody here tonight or this morning.